negative, it's going down. So the electric field decreases and it switches direction. The same as it does with the electric field. So I could put an E here. I could put a B here. This graph will work for both of them. Now, I will say the amplitudes will not be the same, right? They're not even the same units, right? The electric field is measured in units of volts per meter. The B field is measured in units of Tesla. So it seems it's silly to graph them on the same graph. The axis is not the same axis. But what I'm saying is, qualitatively, these things act the same. The electric field and the B field are what we say are in phase. As one is increasing, the other is increasing. As one is decreasing, the other is decreasing. Now, what is different about them, apart from their amplitudes, are their orientation. So these are vector fields, which means they, by definition, are oriented in particular ways in space. So how are they oriented? Well, I can't draw this, but I'm going to try. We'll see if I can do it. I've got to do this in 3 dimensions, which is why it's going to be an issue. But here is going to be my axis. Right? So we'll say that this is my z-axis. It doesn't matter at all what you call them. But I'm trying to show all 3 dimensions. We'll say this is, no, I don't want to call that z. Sorry if I've already mentioned. We'll call this x, we'll call this y, and we'll call this z. Again, it doesn't matter at all. So I'm going to try to do this such that my E field is oscillating in the x-z plane. Right? So you can imagine there's a plane. It would be in the plane of the board, as kind of as I've drawn it here, but not really because it's kind of coming out. But the x-z plane, I'm going to let my E field oscillate in that direction. So that's going to look something like this. So on and so forth. So here's my E field, which I have in green. It's increasing, it's decreasing, so on and so forth. Now my B field, what I've said so far is it's going to oscillate in phase, which means at the 0 points of the E field, those are the 0 points of the B field. At the maximum points of the E field, those are the maximum points of the B fields, vice versa, so on and so forth. I'm not going to try to draw the amplitudes the same because they're not going to be the same. But the B field, if the E field is oscillating in the x-z plane, the B field is going to oscillate perpendicular to that. In other words, in the y-z plane. That will look the best I can do, something like this. Where I tried to draw them perpendicular. I might have failed. Your book has much better graphics than I'll ever be able to draw. But that's the idea. If the E field is oscillating up and down, the B field is oscillating side to side. What's important, apart from up and down and side to side, is that we understand they're oscillating always perpendicularly to each other. There's always a 90-degree angle between the B field and the E field. For this situation where we have accelerating charges that are producing these E and B fields. So, that's the best I can do in 3 dimensions. Now, you might ask, what is the Z dimension? Well, what is going on in the Z dimension? If you'll notice, as my E field is oscillating up and down, and my B field is oscillating side to side here, this whole thing, it seems to be moving in the Z direction as I've drawn, along the Z axis. Right? In point of fact, what I've drawn here is the content of an electromagnetic wave. We looked at the spectrum last time, things like microwaves, visible light, X-rays. Electromagnetic waves are produced by accelerating charges, right? So that's sort of the hierarchy we've been on. Charges produce electric fields. Moving charges produce magnetic fields and electric fields. Accelerating charges produce oscillating electric and magnetic fields that furthermore propagate in a particular direction. That's what waves do. Right? Waves propagate. You can hear me right now because the sound wave is propagating from my vocal cords to your ears. You can see me because light is bouncing off me and propagating through the air to your eyes. Right? That's what waves do. The propagation direction here perpendicular to the oscillation directions of E and B. All three of these things, oscillation direction of electric field, oscillation direction of B field, propagation direction, have to be mutually perpendicular. Doesn't matter if you call them X, Y, Z, whatever you want to call them. They set up a three-dimensional system, which is why the graphics are difficult, because they have to be in 3 dimensions. Okay? Any questions about any of that? Now, I'm in technically section 16.2. The math in section 16.2 is beyond the prerequisite for this course. So we've got partial derivatives here. You may or may not know partial derivatives. If you don't, they're not as hard as they sound. But the math in section 16.2 is a little bit beyond. So I'm not going to go, or a little beyond the prerequisite for this course. So I'm not going to go through the derivation. But I am going to give you the result because it's interesting to talk about. And it's this. No, okay. It's not a T. X. There we go. Time derivative on the right, spatial derivative on the left. Script D's are partial derivatives. If you don't know what that is, it's okay. The point here is, this is an equation that comes out of wave equations. It's actually the solution to a set of equations which we would term wave equations. The equations which describe, sorry, it's not the solution. I'll show you a solution in a second. It's an equation which describes wave motion on a pretty advanced level. But this is what waves do. They propagate through space, right? This is the spatial derivative, as a function of time. When you saw the solution, you've seen the solution to this equation in 1600. I'm going to talk about why. But first of all, let's just talk about this interesting thing where you have this space and time dependence, because waves propagate through space and they're functions of time. Now, what comes out of the wave equation, which is again not something I expect you to know, so this is not something I'm going to test you on, but I want you to see it, is that the speed of the wave, no matter what wave we're talking about, the speed of the wave is found by doing some manipulation to this coefficient, right? So we have two partial derivatives, and we have this coefficient here. So, turns out that process looks like this. For any wave, this is a particularly electromagnetic wave. This works for any wave, mechanical wave, whatever. If you ever want to know how they actually derive the speed of sound in air without running the experiments, you run the math here. So, I realize that this is a little bit nebulous because we're talking about math that not all of you have had, and I'm kind of waving my hands at it, so it's okay. But imagine that you're James Clerk Maxwell in the late 1800s, and you are studying electricity and magnetism, and this is what you have come up with. You have the work of other people like Heinrich Hertz to deal with and to build upon. But you understand wave mechanics because people have been talking about mechanical waves for quite a while now. And you understand that light is a thing, and people have done some experiments and measured the speed of light to be some number, right? But none of that is in your particular focus because what you're doing is talking about electricity and magnetism. And you are doing some work and you come across this equation and you say, oh, well, this is a wave. I don't know what it means, but it's a wave. I can find out the speed for here, and you do the calculation, right? This electric constant, this magnetic constant, you run the calculation, and you get a number which you then recognize without knowing why it's the case as what other people have measured to be the speed of light. And you go, well, that's interesting. But that's not coincidental because physics doesn't really have coincidences, right? People didn't realize that electricity and magnetism fields are what make up what we call as visible light. So in the late 1800s, when Maxwell discovered this, it was actually quite groundbreaking. He didn't actually understand what was going on, but he figured it out. But the idea that this stuff describes a wave which he knew as light was somewhat of a revelation. But this is really interesting to me because in all these other cases, we have not seen epsilon naught and mu naught really working together, right? We've seen them in different places in the denominator and numerator. We've seen them for different constants. But this is a really interesting illustration of the fact that this electricity and magnetism comes together, not only comes together, produces the stuff around us, which we call electromagnetic radiation, but most of it is called light, right? This is visible light. It means it's light that our eyes are sensitive to. We saw last time, there are other kinds, right? But this is where all that comes out. The speed of light is contained here, and if you run these numbers, you get about 8.99 times 10 to the 8 meters per second, which is roughly the speed of light in vacuum, right? In vacuum is important, because light changes speed when it goes into other media, right? Which is why we call this the vacuum permittivity and the vacuum permeability. So all this kind of comes together, and I realize all this kind of nebulous. So if you didn't take notes on this section, that's just fine. I just want you to see it. But this is what comes out of that, this wave equation. So if you haven't taken part differential equations yet, differential equations are somewhat tricky to solve, right? We know how to solve systems of equations like we get in kinematics and stuff like that. The techniques used in differential equations are somewhat different. But one of the things that comes to your advantage is if you can guess a solution, well then that's a solution. Because if you can guess some mathematical function that satisfies this equation, you got a solution. There might be other solutions, but you found one and that works. So what we need for this equation, which we have now kind of figured out, describes this wave, which is made up of electricity and magnetic components, which we call light. We need a mathematical function that satisfies this. In other words, if I take a time derivative of it twice, that's related to the spatial derivative of it twice. Turns out there are several functions which fulfill this, but the most common one is what you have already seen in 1600 as a solution to the wave equation, sines and cosines. So without getting any farther into the obscure mathematics, I'm going to leave that to your DCQ teachers. Let me give you the solution to this equation in the exact manner that your book gives it to you. This, E sub y, which means the electric component in the y direction, as a function of x and t. Let's unpack that for a second, right? So if I were to graph this on a two-dimensional graph, like I did a while ago, leaving out the B field. So it looks something like this, right? Where this is E, and this is T, right? It's actually, the reason I'm doing it is because this leads to a lot of confusion, because what we're saying is that there's an X here, but I don't even have an X here, right? So I could graph it as a function of time, but I could also graph it as a function of X. I just can't show that on the same graph. So when you see this, it's necessarily incomplete. But here's the idea. If this electric field is oscillating in the y direction and also propagating in the x direction, right, where it is has got to be a function of x and also how long it's been propagating. Right? That's what we're saying. I can't draw that because I don't have the three-dimensional skills. No one really does. But that's what we're saying. I have an E field that's oscillating up and down and also propagating in that direction, which means it's going to look like this. Right? Which means this EY, wherever it is in the vertical direction, is a function not only of time, but wherever it is in the horizontal direction. So that's what we mean here. This is the y component of the E field as a function of its spatial dependence x and time derivative t. That stuff appears here. Now what is this? What is E naught? How does that function in this wave equation? Differently asked, but the same answer as a while ago. What is that? That's the amplitude of the wave, right? This is the maximum value that the electric field is going to take. We've seen it oscillates. There's many points where it's 0. This is the maximum value of the electric field. What is omega? I realize for some of you didn't get to this in 1600. I realize some of you it was a long time ago. That's okay. Anybody tell me what omega is? It's what we call the angular frequency of the wave. Right? What is the frequency of a wave? Anybody tell me what that is? It's definitely related to the speed. The speed with which it oscillates, that's getting there. Let's imagine that you're watching a wave pass by, right? So you're watching a wave pass by, and that wave is made up of a series of cycles, right? Waves come from cyclical motion. So let's see. Here's a cycle, here's a cycle. Right? There's two. I gave you 2 complete cycles of that way. Let's say that both of those waves pass by you while you count off 1 second on your stopwatch. Right? So you got 2 cycles in 1 second. Right? That's the frequency. Cycles is not a real unit. So we say the frequency is 2 per second, or 2 over seconds. But nobody says over seconds or per seconds. What do we say? What are the units of frequency? Hertz. It's Heinrich Hertz that I mentioned a while ago. Hertz, capital HZ. It's just a 1 over seconds. That's the frequency of the wave, right? It's how many cycles pass by you per second. Definitely related to the speed of oscillation. Definitely related to the speed of propagation. It's how many cycles occur per second. This is the frequency, generally signified with an F. A script F. Frequency. That is what's called the angular frequency. We got to do a little bit of work on it to make it fit into our trig function. It's really simple. The angular frequency omega is related to the linear frequency F. Just this way. 2 pi F. So if you have one, you have the other. Not a big deal. So that's the angular frequency omega. Where have we seen omegas before? Think about rotational motion. What is omega in rotational motion? It's the angular velocity. Those 2 things are related. You gotta think about it for a little bit. The details are all in University Physics Volume 1, right, which you all had for 1600. So if this is new to you, go back and read some of those chapters. If you need some brush up, go back and read it towards the end of Volume 1 where they start talking about wave motion, and they're going to explain all these things. Or come see me in my office hours. I'm happy to talk about it too. This is the temporal portion of the wave. Let's talk about the spatial portion. You might know what K is. There, okay. So, we'll just go back to the drawing board. That's fine. So I'm just curious. Raise your hand if you did not cover waves at all in 1600. Wow, really? All right. So that okay. Fair enough. We're supposed to. So my apologies for assuming you knew some things you didn't know. Let's just go back to the beginning because I'm seeing a lot of blanks there. That's okay. We'll get there. Okay. Let me graph a wave twice. I'm going to use a sine wave, even though this is a cosine. And since we're talking talking about electrical waves, electromagnetic waves, I'll put the E field here. This one I'm going to graph against the time axis. This one I'm going to graph against the spatial axis. We need both of them because these waves propagate through space and time, right? We've already kind of covered this. Like, here's a cycle and here's a cycle. Let's say that this is 1 second, right? That's what I did a while ago. As I said, 2 cycles are contained in 1 second. So that's a frequency of 2 cycles per second. Okay? This is what we call the linear frequency f. In this case, f would be 2 hertz. I just dropped that chart. 2 hertz. And then we can change that into what's called the angular frequency, omega 2 pi. Okay. So, if I look now at this other graph, which now I'm graphing the electric field as a function of space. Remember, this is all happening at the same time, but I have to put it on 2 separate graphs. We've only got 2 axes. This is how it works in time. This is how it works in space. Well, let's go back to 5th grade science. What am I drawing right there? What is that distance? It is a distance because I'm on a spatial axis, right? What is that? It's okay if you're wrong, just say an answer. You guys know this. It's the wavelength, right? Yes, I see nods. You know that word. It's the wavelength. It's how much of that wave, it's how much 1 cycle of that wave is how long it is, right? This is a wave propagating through space. So if I could see it, I could measure it, right? So I can see it on the graph. That's just a wavelength, right? So we usually symbolize that with the wavelength. Lambda. I can't see the wavelength here because this is a time graph, but I can see it here. But here's how we use that. So if I were to if I'm counting how many cycles of this wave occur in 1 second using my stopwatch, right? And that gets me to the frequency, or I will call it the temporal frequency. I could also measure how many of those waves fit into 1 meter, right? Let's say that this is a meter. Let's say I have 1 meter right there, right? How many cycles did I fit into that meter? 2 complete cycles, right? So that's what's called the wave number, or better, the spatial frequency. So the temporal frequency is how many cycles fit into 1 second. The wave number, or the spatial frequency, are how many cycles fit into 1 meter, right? I'm measuring 2 different things. One of them I'm measuring with a stopwatch, one of them I'm measuring with a meter stick. I'm measuring the spatial dimensions and temporal dimensions. So that takes care of my space and time up here. The angular frequency has to do with time. The wave number has to do with space. I should say that's the angular wave number. It's related to the linear wave number, but we don't differentiate it because we only ever use the angular, right? We use both linear and angular temporal frequencies. We only ever use the angular wave number, so I'm not even going to worry about differentiating with different symbols. We'll just call it K. But that's what this is. It has units of per meters, or meters to the -1. Just like the temporal frequency has units of per seconds, or seconds to the -1, although we usually call that a hertz. We don't do that with the angular, we don't name that after anybody, I don't know why. So all these things are telling you is how many cycles occur per second here, and how many wavelengths occur per meter